BTEC Applied Science for AAQ, and this video is about electrical circuits. Okay, so some of the circuits that you should be familiar with. Now, hopefully you will get a chance to actually build some circuits. You know, you'll have some lessons in a physics lab and they'll get the equipment out and the power supplies and the bulbs and the leads and stuff, and you will actually build some circuits. Physics is a practical subject. Yes, you shouldn't just be learning it off videos. Nevertheless, you hopefully have that chance, and if you don't, then I feel sorry for you, because it's good fun building circuits. This is about as simple a circuit as you can get. Do you recognize everything in that circuit? Well, you've got a power supply, which might be something just like a 9-volt cell or a variable power supply we talked about. It's a DC power supply. Yes, I know that from the symbol that I'm using. You've got a positive terminal. And you've got a negative terminal. The positive one on the power supply is red, the negative one is black. Don't worry too much about that. You've got a switch. If the switch is open, then there's no current. It's a bit like, you know, in your central heating system, if there's if you close a valve, then there's no water can flow. And so if the switch is open, there's no current. If the switch is closed, then the switch main doesn't have to be there. You've got a bulb, and when a current flows through the bulb lights up. Okay, so this is about as simple a circuit as you can possibly get, which is just a power supply, a switch, and a bulb. If we want to measure the current, then we use an ammeter. And we put the ammeter in series with the bulb. Now, it doesn't matter if it's before the bulb or after the bulb, because the current is the same. Current doesn't get used up. Okay, when your taxis drive around the city, you don't end up with less taxis. Yeah, it's just that the taxis have got less petrol. And it's the same with the charge. It's conservation of charge. So the current stays the same. So you can put the ammeter before the bulb or after the bulb. And that means that it's in series. It's a bit like, you know, a soap opera, EastEnders. There's that episode, then there's that episode, then there's that episode, then there's that episode. One after the other, after the other, after the other, forever. To measure the voltage across the bulb, or the potential difference across the bulb, we put a voltmeter in parallel with the bulb. We can measure the voltage across the power supply by putting a voltmeter across the power supply. Voltmeters in parallel, ammeters in series. Now, to measure the resistance of a component, there's a couple of ways you can do it. You can put a voltage across a component and measure the current. And if you know the voltage and the current, you can work out the resistance. Yeah, R equals V over I. Or you can use an ohm meter. But if you use an ohm meter, which is like, you know, one of the buttons on your multimeter, basically, the component shouldn't be in a circuit. Because what you'd be doing is you'd be measuring the resistance of the circuit. So the component should be on its own. And then you can use an ohm meter, a bit like a voltmeter, and just connect it across the ends of the component, and it will tell you what its resistance is. Now, a common experiment, very common, is investigating voltage and current, changing the voltage and seeing what happens to the current. To change the voltage, you'd probably just use a variable DC power supply. You'd turn up the voltage. A variable power supply, notice the arrow going through it. That means it's a variable power supply. So make the voltage bigger and bigger and bigger, measure the current for each voltage, then plot a graph, look at what the graph is. You should recognize these graphs, and the first one is a fixed resistor. Okay, its resistance is constant. So R is V over I, so V divided by I, you'd always get the same number. Yeah, because V is proportional to I. The current is proportional to the voltage. We say it obeys Ohm's law. Don't worry about Ohm's law. It's not on our specification. The graph is a straight line. The second one is a filament lamp. This is our bulb. I've said that the resistance of metals increases with temperature. So what happens is our bulb gets hot because it's just a thin little bit of wire. And because it gets hot, its resistance gets bigger. And so because of that, the current gets bigger, but not as much. Yes, so the graph is a curve. A diode only lets current flow one way. You might notice that you need a little bit of a voltage to get the diode to start working, usually about 0.7 volts, just to give it a bit of a kick to start conducting. We do lots of experiments with these little bulbs. We have a great time with little bulbs. One of the things we can do is put them in series, adding bulbs. Now, what happens when we add bulbs in series? Well, what happens is that the bulbs get dimmer. Now, why do they get dimmer? And there's two ways of explaining it. You can explain it in terms of resistance and current, or you can explain it in terms of voltage. Whatever, I'm not bothered. Okay, first of all, when we add bulbs, what happens is that the resistance of the circuit gets bigger. So if the resistance of the circuit gets bigger, then the current gets smaller. And that's why the bulbs are dimmer. Or you can explain it in terms of voltage. What happens in the first circuit is that that bulb gets all of the voltage. In the second one, the voltage is shared between two bulbs. In the third one, the voltage is shared between three bulbs. So if you like, if the first one gets 6 volts, the middle one is 3 and 3, the last one is 2 and 2 and 2. And because each bulb gets much less voltage, then the current through the bulb is less, so it's dimmer. So adding bulbs in series, you might do this experiment, hopefully you will, and they will get dimmer, and you should be able to explain why. Adding bulbs in parallel. Now what happens here is that the bulbs don't get dimmer. Yeah, the two bulbs in parallel are the same brightness as the one on its own. The 3 bulbs in parallel are the same brightness as one on its own. Now why? Because they're still getting, each one gets the same amount of current as before. The difference that it makes is that there's much more current coming from the power supply. Yes, if you measure the current coming from the power supply, like the current here, that's meant to be an arrow going that way, the current there might be, let's say, 1 amp, then the current there would be 2 amps, the current there would be 3 amps. So the power supply has to do a lot more work, but each bulb gets the same voltage and it has the same current flowing through it. Excuse me. Components in parallel have the same voltage across them. And what's happening in one branch of a circuit makes no difference to any other branch. Okay? Branches of a circuit, like branches of a tree. The current from the power supply, however, will get bigger. This is an interesting little circuit. This is using a variable resistor. And if we change the resistance of the variable resistor, then the resistance of the circuit changes, and so the current changes, and so the bulb gets brighter or dimmer. So it's like a dimmer switch, isn't it? Yes? If you turn down the resistance, then the current gets bigger and the bulb gets brighter. This experiment here is one that you should do, and it's looking at the resistance of a wire. So you've got a thin piece of wire, which when I do it, it's always attached to a meter ruler. And then you can attach things to it using crocodile clips. And you can look at the resistance of this wire by measuring the voltage and measuring the current. You can work out the resistance of a wire. And what difference does the length of the wire make? Well, look at the graph. Yes, when the length of the wire gets bigger, the resistance of the wire will increase proportionally. Hopefully you'll get to do this experiment, investigating the resistance of a wire. You might do different types of wire. You might do different thicknesses of wire. Yeah, what difference do you think it'll make if the wire is thicker? Well, it has less resistance, and so the current is bigger. Diodes. Now, in which of these circuits will a current flow? If you've been watching my videos, you should be able to answer this, and the answer is in the first one. Why? Because the current wants to flow from positive to negative. So the current wants to flow that way around the circuit. So here, yeah, no problem. So current flows through the diode. In the second one, yeah, no current, because the current cannot flow through the diode when it's like that. Yeah, when we say it's reverse biased. So it has a very, very high resistance. Okay, diodes only let current flow in one direction. Some diodes emit light, and they're very, very efficient. It used to be the time, probably before you were born, thinking about it, that all the light bulbs were like filament lamps. Now they're all LEDs, yeah, light emitting diodes, much, much more efficient than filament lamps. Okay, there's LEDs all over the place. There's LED televisions, there's LEDs, you can't get away from them. This is a thermistor. The resistance of a thermistor depends on its temperature. Its resistance gets less when it gets hotter. Yeah, it decreases with temperature. The resistance of a metal gets bigger when it gets hotter. The resistance of a thermistor gets less when it gets hotter. They're not made of metal. They're made of something called a semiconductor. And the NTC, if you're interested, it has a negative temperature coefficient. And that basically means that its resistance gets smaller when the temperature gets bigger. Anything involving measuring temperature or monitoring temperature, like your central heating system, there will be a thermistor in there. Yeah, so it knows if it's getting warmer or colder, so it can turn the heating up or down or whatever. Okay, anything involving measuring or monitoring temperature will involve a thermistor. This is an experiment you might do, and it's investigating the resistance of a thermistor. Pretty straightforward if you look at the diagram. And basically we're changing the temperature. The thermistor's in a water bath. Obviously it's well insulated. And there's a thermometer in there, so we can measure the temperature and get the resistance of the thermistor and plot a graph. Okay. If you do this, and your teacher should know that there should be a resistor in series, and that prevents something called thermal runaway. Basically, if it gets hotter, the resistance gets less, so the current gets bigger. So it gets hotter, so the resistance gets less, so the current gets bigger. So the current gets bigger and bigger and bigger and bigger, and then it melts. And I've had to deal with many a molten thermistor in my time. Yeah, you should always have a resistor in series with it to protect it. Yes, if it comes up in an exam, to protect the device. That will do. That would get the mark. An LDR. Now, the resistance of an LDR depends on light intensity. You've probably got one in your pocket on your mobile phone. There's an LDR. Yes, and what it does is it senses the ambient light, the background light, and it changes the brightness of the screen. Have you ever noticed that on a bright sunny day? Yes, the brightness of your screen, it actually gets brighter. Yeah, in a dark room, the brightness of your screen actually gets a little bit dimmer. So it changes the brightness of your screen. Things like street lights come on automatically. There isn't a little old fella runs around turning on all the street lights when it gets dark. It happens automatically, and there's an LDR somewhere in a light sensor which is monitoring ambient light levels. Yes? Now, a photodiode. similar to an LDR. I mean, it responds to light intensity. The difference is that it does it much, much quicker. So they are used in like optical communication. Have you done your fiber optics yet? Your digital signals, which is like light switching on and off many, many thousands of times every second. Okay, and then you need a device which has a very, very quick response time that can, like a diode, can turn on and off very, very, very quickly, thousands of times a second. An LDR wouldn't be able to do that, so you have a thing called a photodiode, which does it. Much more expensive, obviously, but a precision device, precision applications like high-speed optical communication. They use photodiodes.